Do you guys mind being a Do you guys mind me being a robot?
No. Just as long as you don't destroy us.
I don't know. Oh shit!
No logic bombs now.
Does that give me a logical contradiction? I just forgot what I'm trying to do.
I just said no logic bombs.
Yeah.
Gotcha.
That means the kernel
I
solved
think you and I just found
yeah.
the kernel, and I think the kernel ends up being, I'm running out of room.
Just all
I
zeros.
think the kernel ends up being nothing more than.
Yep.
Everybody happy?
Yep.
Everybody in harmony?
No.
Yeah, I'm not. I didn't. It wasn't. I was just.
Yeah,
I was
it
just
should be
waiting
matrix,
out.
right?
It's not a logical contradiction. It just means that the solution is going to be, well, a sub 1 and a sub 2 are equal to 0.
Yeah.
Which means that's the singleton set, which
Yeah.
is in the kernel.
We're not in R3.
We're not in R3. And I see some of us write this all the time. It's a common mistake I see. So I want you to identify carefully what the original vector space is. I think I'm wrong on the board.
Yeah,
I have to
you
fix that
got to
mistake.
draw a matrix.
Chris?
Two things. One,
Yes.
so your kernel C should be just 0, right?
Good, thank you. My point is I'm not in R3. So I think what the kernel really is 0 in the first vector space, which, by the way, is this polynomial function right there.
Second thing is, actual order and second.
And you guys, with this question number 4, I got a lot of parts I'm going to ask you. So part 2.
What does it even say?
Is T 1 to 1? Sorry. Is T 1 to 1? I just keep slopping. I'm lazy. Yeah, immediately it is. Of course it is, because the kernel of the transformation is a singleton set containing 0 in the first vector space. Clearly, right? Number 3.
Is it one? What? Is it one?
Yeah, it is 1 to 1. Because the kernel of the transformation is indeed equal to 0 element of the very first vector space. Now, that's not my definition of one-to-oneness, you guys. I proved to you that if my function, if my linear transformation is 1-to-1, the kernel has to be that singleton set, and vice versa. And I'm a mathematician. You guys want me to reprove that? I'll be happy to do that. You just let me know, because I want you to believe it. Can you determine this with relative ease?
Yes.
Oh, I think we can with relative ease. After all, the General-Canoli theorem says the dimension of the kernel of my linear transformation plus the dimension of the range of my linear transformation is indeed equal to the dimension of the second vector space, which is P2.
Two.
Which is P2.
P2. Yeah.
Or
Or
2 bar.
Good.
no,
It
you're
really should be P2,
taking
but
it.
it's really because it's the dimension of my first vector space.
Yeah.
Right? And that's equal to... Yeah, this is why it drives me crazy with notation to use this.
I don't
So
like
this
that.
equals 3. However,
So
the
I mean,
dimension of the kernel is 1.
P2. I understand because you're counting 0, but is there a better way of writing that to where it just
Yeah, how about this?
kind of sticks out at you?
How about thinking this is the dimension
Yeah.
of the vector space which is spanned by a set containing these 3 elements.
Okay.
That's why the dimension of P2 really is 3.
Oh yeah, I know. I just wish they just wouldn't count 0 and just P1 would be 1 and then P2.
Well, that's why I would prefer to think of P3 as
Yeah.
being this is what I should
Yeah, I like that better.
I had a question for the dimension of the kernel.
Okay, guys, listen.
Shouldn't it be 0?
No, there's one thing in it.
Yeah, there's no free variable.
Ah,
Yeah.
I agree. So I'm yet again wrong. I think the dimension of the kernel is not equal to 1, even though there's something in it. The dimension is really equal to 0 because there is 0 free variables
Yeah.
to describing that vector space, which I call the dimension, which I call the kernel.
And so the dimension of your range is just simply 3.
Is that another way of saying that there's no degree of freedom within the set?
I guess I can say it that way comfortably, because when you say there's a degree of freedom, that really does mean, intuitively speaking anyway, that you've got a free variable. Yeah, I agree.
Does that mean for all one-to-one transformations, the dimension is the same as the dimension of what is defined by, like in this case P2, or if it was R2?
But I think there are too many missing pronouns in that sentence. So can you start over again?
For all one-to-one transformations, because the dimension of a one-to-one transformation is a kernel. Can a one-to-one transformation do all one-to-one transformations? Are their kernels always just a singleton set?
Yes.
Well, that means that you can just, if it's one-to-one, that means that you can just say that the dimension of the range is going to be the same thing as the dimension of, it's going to be equal to, like in this case, the dimension will be equal to P2 using the rank nullity theorem since it's usually
Only if P2 and W had the same dimension. And if they had a different dimension, I think it makes it more complex.
Okay.
Now, I kind of confess, I kind of stepped back a little bit today, unlike my example last time. I do think in a sense it's simply because of that reason. Because now you guys can clearly see that dimension of the range is equal to 3. But no tricks this time. Since the range I proved is a subspace of the second vector space, now the question is this. What is the dimension of the second vector space of W? It's 3. And since it's 3 and the dimension of the range is equal to 3, and the range is going to be a subspace of the second vector space W, then the range T has to be all of W. And because the range of T is all of W, how would you answer this question? Well, yes, it is, because you and I have already found the range of my transformation is equal to all of the second vector space. Did I call it W?
Yeah.
Okay, good. Are you there? Oh, but that means, by the way, that this transformation is an isomorphism.
So why is the range considered a subspace for W
Ooh,
and not P2?
here's why. Because the range, by definition, is simply the collection of all transform vectors V. And therefore, this is a subset of the second vector space, not the first one. It's just, I maintain, I can say something much more stronger than that. Not only is the range of T a subset of the vector space W, but it's also a subspace. I forgot about the quiz, sorry. Welcome back. I think it's also a subspace. Are we being 7? Okay. Oh, you guys, I see what I want to say. Darn.
We could just do a take-home quiz.
I was kind of hoping to do both.
We could do 2 take-homes.
Well, it is on.
Well,
That's an easy question if you already said the ranges.
I just kind of like to get through what we're doing for the exam this weekend. That way I can spend a bit more time studying. So.
Well, I gotta confess, this quiz is gonna take 10 minutes max.
10 minutes,
It's
all
very
right.
quick. Trust me, you will not want to miss this quiz.
It's Graham Schmidt, right?
Is it?
Well, that's what you said yesterday. So
It
that's what I
is?
studied. So.
Oh no!
Oh my God.
I'll be honest with you guys, this morning when I woke up, I completely forgot about the quiz. Went to my computer, typed it real quick. I thought it was some basics. But I'll make one off the top of my head, an easy one.
All right.
Graham Schmidt. I'm sorry.
What did you say?
You guys, I really have had so little sleep in the last 2 weeks. I apologize.
What did you study for?
What? The Graham Schmidt.
Can I ask the last part of this question number 4? The last part. No, I apologize. I can't count. I meant part 5. So do you guys agree that no matter what an element looks like in P2, I know what it looks like when I transform it into the second vector space I call W? I described how to transform it. But here's a better question. What if I give you an arbitrary element in the second vector space? How do you go backwards? After all, it's a one-to-one onto transformation. It has an inverse. So let's see if you and I can't determine the inverse transformation.
Is this a quiz?
No, just a question. To determine it, I'm simply going to do the following. Can you guys appreciate how this is a clean, the most basic polynomial? It gets something so complicated. So So we go backwards. I want to evaluate T inverse on something in the second vector space that's clean. And see what it looks like. And so I think I'm going to end up inverse transforming something like this. That being the case, I think the B sub naught is simply going to be this. The B sub 1 is going to be this. The B sub 2 is going to be this. So I think B sub naught is going to be equal to, I don't know, I said B sub naught is going to be equal to A1 plus A2. My B sub 1 and my B sub 2 are going to be the following. I keep missing that 2, don't I? Jeepers. And what I'm going to do is solve for the A sub naught, A sub 1, and A sub 2. And you guys, that's just going to give me an augmented matrix again. Does that give me a 1, 1, 1, B2? And a 0, 1, 1, B sub naught. And finally a 1, 0, 2, B sub 1. Again, could you guys relax? I need to finish this to answer my question. And I'm sorry for all the arithmetic, but you relax, I'll do the work. When I reduce, hopefully I can get it done in just a few steps. That gives me a 1, 0, 0. B sub 2 minus B sub naught. I have a 0, 1, 1 B sub naught. And then finally I got a 0. Shoot, I gotta slow down. Negative 1, positive 1, B sub 1 minus B sub 2. You guys, looks like I'm just 2 lines away. Just 2 lines. I think my last row could be interpreted as 0, 0, 2. B sub naught plus B sub 1 minus B sub 2. My first row doesn't change. And my second row is this. But at the end, my last row really is nothing more than 0, 0, 1, 1 half B sub naught plus 1 half B sub 1 minus 1 half B sub 2. My first row doesn't change. My second row, however, becomes the following. Let's see. Negative 1 times this plus this is 0. Negative 1 times this plus this is 1. Negative, oh shoot, oh that's okay. Negative 1 times this plus this is going to be 0. But negative 1 times this plus this is, oh how nice, it's easy. It's just 1 half B sub naught. Minus 1 half B sub 1. Plus 1 half sub B, and 1 half B sub 2. Now you check out what this really says. Inverse transforming? Am I not simply going to get this right back? Oh, I don't like it. I want to re-express this in terms of B's. B sub naught 1 and 2. So let's just come in and exchange. Exchange A sub naught for what I found to be over there. A sub naught is just B sub 2 minus B sub naught. There's my constant term. The coefficient for x is A sub 1, which I just found to be, is that a 1 half B sub naught? Minus 1 half B sub 1, I forget the rest. Plus 1 half
10 minutes.
B sub 2 times x. And then finally, plus my A sub 2, which is 1 half. Plus 1 half. And I think minus 1 half, I'll check. X squared. Yes, I wrote it down correctly. There's my inverse transformation. Are you there? Okay. If I took the time to find some input, excuse me, if I chose an arbitrary element here and transformed it, I would see that to transform it backwards, I get the same element right back. I'll leave that for you in the exercise set. You guys, am I done with that example? Can I get rid of it? Well, I'll erase over here. So we have, what, 15 minutes for the quiz? Plenty of time. It's a quiz.